Okay, so here we're just looking at some of these kind of reactions with the the formation of esters, esterification, right? So with fatty acids, that's very applicable because if you take a fatty acid, a carboxylic acid, and you react it with an alcohol, you'll be able to cause the esterification. You're going to create that ester group that's going to get added to this glycerol, usually molecule, and then you'll have these ester groups with these fatty acid chains coming off of them, forming these glyceraldehydes. Okay, so addition at double bonds. So some fatty acids have double bonds, right, or triple bonds, and you can cause these addition reactions with the hydrogens at those double bonds. For example, here, if we have linoleic acid, which has these two double bonds within it, okay, and using hydrogen and the catalyst nickel, okay, we can cause these double bonds to break, and then we'll be able to add hydrogens at each carbon there, the addition reaction, and then we'll change it from linoleic acid to stearic acid. Okay, which will be an 18 carbon acid. So here, this 18 carbon diene changed to just the straight chain acid, stearic acid. Okay, these would become unsaturated fatty acids. The unsaturated fatty acid can become a saturated fatty acid, breaking that double bond. And this is used in the food industry, right, to change some of these fats from one melting temperature to a new melting temperature. Okay, so and oftentimes we hear those unsaturated or saturated fats in our food. Okay. All right. So glyceride is a 3-carbon molecule with alcohol groups attached to it. Okay, and so if we want to, we can attach to those glyceride molecules. We can attach the carboxylic acid groups, so you can get that esterification, and you could have it occur at each of these alcohol groups. Sometimes you have all three, sometimes just two, sometimes even just one. Okay, but once you get that attached, you can also cause the hydrolysis of that ester group, once again using water. And in the presence of an acid, remember, in the presence of an acid, we are going to form the acid. If this was a base, we would form the conjugate base. But we're using acid here, so we're going to go back to the fatty acid. When we cleave here, okay, we're going to allow that acid to come off and an OH to go back on. Okay, so we'll be able to put those back into a glycerol, and the fatty acids will come off. Okay, so that's through acid hydrolysis or water hydrolysis in the presence of acid. Okay. Saponification is base catalyzed hydrolysis. So base catalyzed hydrolysis is going to form the anion, the carboxylic acid anion, the conjugate base. And because it's an anion, you can actually cause this salt to be created, right? So the products of this reaction are, once again, an alcohol, like we'd expect, and the ionized carboxylic acid salt, which we would refer to as soap. Okay? So these soap molecules can have these long, uncharged hydrocarbon tails, but then they also have these negatively charged carboxylate groups that are able to interact with excuse me, polar things in water. Most specifically water, because that's what we want. Okay? So when you create these ionized carboxylic acid salts, these saponification soaps, then they're going to have these polar heads, and on the ends of them you'll have these long nonpolar tails, and it's the nonpolar tails that can dissolve grease. So your greasy plate, you can't wash it because water won't interact with the grease, so you put some soap on it, and what happens is this long hydrocarbon tail, which is nonpolar, interacts. So if here's my greasy molecule, okay, this is my grease, this nonpolar tail will interact with the grease and it'll start to surround it. Okay? And so it's going to surround it with these nonpolar parts, and it's going to create what we call a micelle as it surrounds it. It's like almost like a membranous cell that goes around that particle. And then, because all the nonpolar parts are facing inwards towards the grease, and the polar sections of the soap are facing outwards, now you have a whole big particle here that essentially on the outside of it is polar, and water can surround that. And then it can dissolve it and wash it away. Okay? So it forms those micelles that dissolve the oils and the dirt particles. And then the water can interact with the polar sides and wash it away. Okay, so looking at the saponification here, when you have that ester group, you're going to cleave that. You're going to put this hydroxide back on to the alcohol, and then you'll be left with the acid conjugate, which is the anion, forming your salt, which is the soap, okay, and an alcohol. Okay, so living in San Antonio, this is a common problem, hard water, right? You guys have heard of hard water, right? So hard water, when you have hard water and you use it with soap, then your soap molecule is an anion, and your hard water has these cations in it that can interact with that. And those anions with that cation form precipitates, which are insoluble. I guess they're insoluble precipitates. They won't be dissolved by water. Okay, and they create these hard films on stuff, on your dishes or on your bathtub or on your shower, right? Get this hard kind of layer of this calcium ion stuff, right? That's because those calcium ions are reacting with the soap ions, which creates an insoluble solid product. So when they talk about softening your water, that has nothing to do with less ions in your water. It's not a filtration process. It's a transfer process. In fact, when you soften your water, you add more ions to your water. Because what you're doing is by adding more of one type of ion, you're pushing another type out. So it basically, if I saturate my water with sodium ions, then it can trade places with the calcium ions, and the calcium ions can be drawn out. because the sodium ions are basically like pushing them out. And so you have actually a higher concentration of salt in your water when you soften it than it had previously. So sometimes actually if you have really hard water, to soften it, you have to have kind of a high concentration of salts that are pushed in, and your water can actually taste salty. And you're like, well, wait, this is, I thought this was like a purification filtration process. It's nothing like that. That's not what it is. It's a transfer of one ion for another ion. Sodium ions are on the very first column of the periodic table. Metals of the first column of the periodic table, the alkali metals, are insoluble metals. So if you put a sodium with this salt from the soap, it will just wash away. It'll be soluble. But if you put a calcium on that soap, it becomes a solid, insoluble precipitate, and it precipitates out. And then it creates a film all over everything, right? So that's what we mean by softening water. And the same thing can happen from like shampoo with hard water, right? You're creating that film on your hair, basically, instead of it just washing off. If you use softer water with sodium ions, it won't create that film on your hair. So your hair could, if you're using hard water, it feels more stiff and brittle almost. But if you have the softer water, it just washes all that soap off, and it doesn't precipitate those calcium ions onto your hair, or onto your shower, or onto your plates, or your cups, or whatever, right? So in San Antonio, we have this problem because our water comes from an aquifer, and there's lots of calcium ions in the aquifer, right, that are getting into our water. Okay, now phospholipids. These phosphoglycerides are glycerol molecules, the 3-alcohol glycerol, and then you also have a phospholipid that's attached to that, and it creates these phosphoglycerides. Okay, these are very important molecules. Okay, so with these, you're going to have the glycerol, the fatty acids, and the phosphoric acid with an amino alcohol attached. Okay, and replaces the end of a fatty acid, of a triglycerol, with a phosphoric acid. Okay, so these phosphoglyceride properties, they have hydrophobic and hydrophilic domains, which kind of makes them like these soap molecules, which have hydrophobic. What does hydrophobic mean? You have a phobia of water, right? You're afraid of it. Okay, hydrophilic means what? You like water, or technically you love it. You're in love with it. Okay, if you're hydrophilic, okay, you're water loving. All right. So hydrophobic, you have a phobia of water. Hydrophilic, you're in love with water. Okay. So these phospholipids have both domains, the hydrophilic and hydrophobic, which give them kind of that property that could create micelles, and those sorts of things, which is going to be very important biologically, because this is how cellular membranes are made. Okay? So these are the structural components of membranes. They can be emulsifying agents, which makes sense because just like your soap is an emulsifier, dissolving fats, okay, these phospholipids can also act in that way and be emulsifying agents where they dissolve fats and are washed away in water. Okay? So they can be suspended in water. They spontaneously rearrange into ordered structures. So what's going to happen if I have something with a polar head and a nonpolar tail, and then something else over here with a polar head and a nonpolar tail, and they're in water? Well, this part is nonpolar, and what is it trying to do? It's hydrophobic. It's trying to get away from water. Can it? it's just in water. It can't really get away from water. So what it does is it finds these other nonpolar things, okay, and they start to interact. So if you had a bunch of these around, okay, then they would all kind of spontaneously come together. Their nonpolar ends would start to come together, and the polar ends would go outwards to be around the water, and the nonpolar ends would come inwards away from the water towards themselves so that they would interact with one another. And that would be a spontaneous process, creating that micelle that we talked about, spontaneous micelle. Okay? Okay, so the phosphoamino alcohol is highly hydrophilic, water-loving. These are used in cellular membranes, micelle formation, okay, emulsifying. So we have two types, one made with a choline and another with a lectin. So here we can see some of these examples. Seriously? Isn't it clearer? No? Okay, so you can see here are these hydrophobic tails, which are carbon chains, right? And this is the phospho ester head that's created. That's the phosphate group. Okay, here's another one, another example. Okay, this is the lectin example. Here's the phosphoester at the head, and then these are kind of the nonpolar tails that are created. And so you're creating these groups that would interact with nonpolar things and with polar things, which are going to be essential to cellular membrane creation. Okay, so you can see they're all pretty much the same, except for kind of how this phosphoester group is, the R group there, the phosphoester, is slightly different.
So the heads are polar and the tails are not polar.
Exactly. Okay. So like even within this head right here, you can find like this polar nitrogen. This has a polar nitrogen. The phospho groups are polar. Here I have a polar nitrogen, and also these acid groups here, which are polar, and then the phospho group, which is polar. So this bottom one has highly polar there. Okay. And that would be highly hydrophilic, whereas these tails would be extremely hydrophobic. Okay, and we're creating these two different parts to our phospholipid. Okay. Okay. Okay, so these phospholipids are glycerol lipids, meaning they're part of the glyceride alcohol substituent, okay? But then you also have some lipids which are non-glyceride lipids, like these sphingolipids, okay? These are based off of sphingosine, all right, which is a long-chain nitrogen-containing alcohol, okay? Which is also a lipid. Okay, they also have the polar heads and the nonpolar tails. So they're amphipathic, having both parts to them. Okay. So structural component, these are structural components of cellular membranes as well, but then the phospholipids are really what going to create the cellular membrane, and these can be kind of embedded parts of that. Okay. All right, so we have two major categories, sphingomyelins and the glycosphingolipids. All right, and you can see all the polar parts and then the nonpolar tails that are being created. Okay. So, have you heard of myelin sheaths? Do you guys know what those are? Those are around the nerve cells, right? For nerve propagation, they help with that. So these sphingolipids can be structural components of those the lipids of the nerve cell membranes, right? And that would be like these to create the myelin sheath, which is kind of like this sphingomyelin, right? Sphingomyelin. So that would be a component of that type of cell membrane. All right. Also in the brain, cerebrosides. So you have glucocerebrosides and galactocerebrosides, right? These polar sugar molecules attached to these sphingolipid membranes. And they would be parts of those brain cells, okay? So which messing with nerve cells and brain cells, causing deficiencies in these types of lipid membranes would lead to different types of diseases, as you can imagine, like Tay-Sachs, Gaucher's, Krabs, okay? These would all be a result of deficiencies in the enzymes that process those types of lipids. Okay, steroids are another class of lipids. So you guys often hear steroids and you're like, right, somebody's taking steroids, or that they're on these drugs that are going to make them strong. That's not the only kind of steroid. That is a type of steroid, but steroids are lipid messengers. That's what they are. They're hormones. They're lipid hormones. And growth hormone is a type, okay, but it's not the only type. And so steroids are synthesized from these basic carbon skeletons. So this is the basic carbon skeleton of a steroid molecule. We call it the steroid nucleus, okay? And as you change parts of that steroid nucleus, you'd get different steroid hormones or molecules that would act as messengers. The nice thing about a steroid messenger hormone is its ability to act quickly to cause a response inside your body. Because if you have a cell that has a lipid membrane, that lipid membrane prevents things from passing from the outside of the cell to the inside of the cell. So usually you need like a receptor or something like that for those things to pass through. But steroids, because they are lipids, they can just go right through your membrane. So they don't have the same security measures, I guess you could say. And so they can act more quickly and get to your DNA to cause a cellular response more quickly. Okay? So that's kind of the benefit of having steroid type molecules available. Okay? Cholesterol. We find cholesterol in our blood, at cell membranes. Okay, these are precursors to bile salts, which are emulsifying agents. Right, emulsifying agents are going to have polar and nonpolar parts to allow for you to be able to dissolve fats. Okay. They are also found as male and female sex hormones and adrenocortical hormones. Okay. All right. So bile salts are important in lipid digestion. So the dissolving of those lipid molecules. Okay. So here we can see this is a cholesterol nucleus. Okay. And then attached to that are these different groups, which would make it a different type of molecule. So here is a cholesterol molecule. Okay. here is testosterone, which is also a steroid molecule. Progesterone is a steroid. Cortisone is a steroid. So now when you hear the word steroid, you have a better idea what that actually means. It's an actual lipid molecule. It's not a straight chain lipid, right? But it's a nonpolar fatty molecule hormone, essentially. Okay? And you can see that you'll have different groups attached to them, to these steroids molecules, which will give them different properties and be recognized different, allow them to be recognized differently. Essentially, the one hormone will have a different job than another one. And so they'll go off and do different things. Okay? Okay, so some of these steroid hormones, like the adrenocorticoids, we have two groups, like mineral corticoids regulate ion concentrations. So filtration, ion concentrations and filtration at your kidney, right? If you're going to retain those or get rid of them. Glucocorticoids enhance carbohydrate metabolism. So cortisol, which we saw earlier up here, right? That's cortisone, sorry. But cortisol would increase glucose and glycogen in the body. Okay? So with its ketone derivative, cortisone would be an anti-inflammatory, cause anti-inflammatory responses. Another derivative of that cortisol would be prednisolone. I can't say that. Prednisolone. I don't know who names these things, by the way, but which would have both asthma and inflammatory responses as well. Okay, I always have a hard time with that one. Prednisolone. How are you going to say it?
Prednisolone.
Oh, prednisolone. I like it. Okay.
More often it's called prednisone.
I see. Okay, so those are both going to have anti-inflammatory responses and could help with like asthma and things of those natures. Okay, waxes are also lipids. So when you see a wax molecule, you're like, okay, that's not really organic, right? But it is. That's an organic molecule. Waxes are lipid molecules that are made up of carbons and hydrogens and oxygens, and they're fatty, right? They're greasy, waxy, nonpolar stuff. And so that's going to be a lipid particle. So these waxes are also like these carboxylic fats, these acid fats. They're going to be esters. Okay. Use one alcohol instead of a glycerol. So instead of having a reactant with a 3-alcohol carbon for these fatty acids, you're just going to have one alcohol. So they're going to be long-chain fatty acids and long-chain alcohols. So you're going to create that ester group with 2 long chains on both sides of it, okay, for these waxes. So you can see here's some example of some of these waxes. This is the long-chain carboxylic acid. This was the long-chain alcohol. So those are really long chains, right? 29 carbons, well, which would be 30 on that one side of the alcohol side. On the acid side, we have 16 carbons on the acid side. Okay, so that's a really long thing with that ester group kind of not necessarily in the middle, but pretty embedded within it. Okay, so this one right here is beeswax. That's your beeswax molecule. Here's a whale oil, which is a waxy thing as well. So 16 molecules over here and 16 on that side. 16 on both sides. Carbons of the ester group. Okay, so those are our waxes. Complex lipids So, like I said before, complex lipid is not a lipid molecule that is complex. It's complexed with other things like proteins and things like that. Okay, so that's what we mean by a complex lipid. So they're those bonded to other types of molecules. So we have things like lipoproteins. So you have a lipid and a protein making the lipoprotein molecule. These are found in blood. So these lipoproteins can be surrounded by layers of phospholipids, cholesterol, and proteins. And you're making a complex. Okay? So these might be familiar to you. Okay? These classes of these complex lipids like VLDL, very low density lipoproteins, LDL, low density lipoproteins, and HDL, high density lipoproteins. Okay, so these can actually be measured in your blood to specific ratios of how much you have of one or how much you have of another, and they can often be identified as markers kind of the health of your health as well. So, all right, so these are our types of lipoproteins. The chylomicrons, very large, very low density, okay? And they transport from the intestine to the adipose tissues. So that's where you're going to get some of your fats and things being deposited in adipose tissue for storage. Very low density lipoproteins. They are made in the liver and they transport lipids to tissues. So if I want to bring tissues or fats to my, from my blood into my tissues, then I would use these very low density lipoproteins. Okay? Low density lipoproteins would carry cholesterol from the liver to tissues. So remember that cholesterol was one of those steroid molecules that we can carry. Okay, and high density lipoproteins also made in the liver, and they scavenge excess cholesterol from the blood. Okay, so you know what, we'll just look at those more closely next class, the complexes of those.